Supervised learning. Data often has a topology. If we want information about the topology, that's called unsupervised learning. But our goal very often is to make predictions using a topology, and that's supervised learning. So we're going to look at functions as layers to begin with. So we have a function model has variables and parameters. And often a function is called either a transformation or a mapping. But we want to look at an interpretation of a function as a layer. So independent variables are inputs to the layer. Dependent variables are outputs from the layer. And the parameters are regarded to be internal to the function or in the layer. The forward direction activates the function on instances of the variables. We regard the parameters as fixed during activation. This is called feed forward or activation. The backward direction trains the parameters given instances of the variables. So here we think of the inputs and outputs as being fixed, and then in the backwards direction we use derivatives to change the parameters. This is called backpropagation or sometimes gradient descent, depending on the algorithm. Supervised learning means that the parameters are estimated with data of the form X's and Y's, in other words, the data you need to clamp the inputs and outputs with instances, labeled data. In other words, if training data has the form of features and labels, then we say that the data is labeled. Supervised learning means using labeled data to estimate parameters. So let's look at some data. Calculus students, college calculus class, take 4 exams in the final. Each are out of 100 points. And then we'll have a variable pass, which is 1 if they get an average of 70 or better and 0 otherwise. Here's our data. And of course, exam 5 is the final exam. This column previous is 1 if the student had calculus earlier, high school, or they're repeating the course, and 0 otherwise. We could do regression, use previous in the 4 exams to predict exam 5, or classification, use previous and the first 4 exams to predict if the student passes the class or not. We're going to do the latter. Our goal here is going to be predicting if a student passes the class from the previous column and the first 4 exams. And the idea here is we're predicting if they're going to pass before they take the final exam, maybe as a way of identifying who maybe needs some intervention. Here's the data. Here are the variables and our model, the layer. Often, however, we define the model in a special form. It allows us to do something clever. We take the parameters and make them weights on the edges. We take the internal variable as the sum of all these parameters and variables. And notice beta sub I here is the constant, or sometimes called the intercept parameter. We have an activation function, and then we do a little revision of this concept. First, we take a constant input of 1 and associate that with the intercept vector beta sub I. Then we define an internal variable, capital Z, which is a linear combination of the variables. And then we have a activation function that's a function only of one variable. So our function model looks like this. This is what's known as the sum and fire model. Kolmogorov showed that the sum and fire models are sufficient, and he actually did this in his proof of one of Hilbert's problems. We'll see this later on in the course. But we have to now choose a suitable activation function. It's got to be continuous in the forward direction. That's because of Hilbert and Kolmogorov. We'll see that later. And it must increase from 0 to 1 over z because it's modeling the variable pass. So here we have y as a function of z, has to go from 0 up to 1. But we can't use that model, it's not continuous. Its antiderivative, however, is continuous. And in fact, this is what's known as the ReLU function, the rectified linear unit. It's incredibly important, in part because we actually get convex region above the ReLU in what's called its epigraph, which means that the ReLU is a convex function. And we'll look at the ReLU function in depth later on in the course. Unfortunately for now, it's not what we want to use because it doesn't go from 0 to 1, it goes from 0 to infinity. So we're going to look at the logistic function. This is a function 1 over 1 plus e to the negative z. As z goes to infinity, e to the negative z goes to 0, and we get 1. And we have symmetry about the y equals 1/2 there. So if our linear combination of variables, our capital Z, is less than 0, then the probability of being in class 1 is less than 50%. If the sum is greater than 0, the probability of being in class 1 is greater than 50%. In other words, we have a function that transforms to linearly separable model. So here is my model, the logistic function. Training means I learned the beta sub k's such that the linear combination is less than 0 for class 0 and it's greater than 0 for class 1. Now we'll look at the actual training algorithm later in the course. Right now you just need to know that this is how we pick the betas. And this process is known as logistic regression. So let's try it out. We'll use scikit-learn. First, we need to explore the data. So here is previous in exam 1 and exam 2. Notice most students have not had calculus previously. And these two histograms show that there are two very different but overlapping populations of students. And in fact, we see that with all the data. Our goal is to predict pass after the first 4 exams, so we don't want exam 5 in this at all. So then we're going to import the logistic regression model and load our training data. And we're going to drop exam 5 and pass from the X values of the training data because the pass variable is in the Y part of the training data. Now, scikit-learn has a very simple methodology. You create the learning object, you fit the object to the data, you analyze the results, now stored in the object itself. So there's the first two, the logistic regression. We create it, ask it to do a fit and intercept, and then we fit the classifier object to the data. And then we test not with the original data, but with a new data set. And in fact, there's a test set of calculus data. We drop exam 5, split off the features, just like we did for the training data. And then we score the classifier on the test data, which gives us an accuracy on the test data of 93%. So logistic regression implies linear separation. Let's look at what would happen if we restricted to only exams 3 and 4. So here's the data for exams 3 and 4, and it's not separable. You can see that there are blue dots and red dots mixed in together. But we're going to look at the decision surface for logistic regression. And a decision surface is the probability of being in class 1 at every point in the feature space. In this case, the XY plane, because we only have 2 features. And this is what our decision surface looks like. This is actually a graphical image of a predictive model. A predictive model assigns a probability to each point in space. Clearly, this data is not linearly separable. But a logistic regression assumes linear separation. Well, at what cost? Well, let's define a margin. So those between 20% and 80%, it may be hard to say if they're class 1 or class 0, if they're going to pass or going to fail. And you can see the margin corresponds in our decision surface to a very large region. This is what's called an absolute margin, where you only have certainty in your predictions, and you can see that it's very large. So logistic regression is an equation model. It has low model complexity. It has high bias, and it often implies a large margin, as we see here. So let's look ahead. Most predictive models, the ones the machine learns, are algorithm models, functions defined by algorithms. And even when we use equation models, the parameters tend to be estimated from data via algorithms. But most equation models in predictive modeling are defined by layers, often integrate and fire layers. And notice I used sum and fire earlier. It's actually integrate and fire because, yes, the sums do in a limit become integrals. So supervised learning is often via algorithms for estimating parameters with a focus on the backward direction. But what is an algorithm? Well, a sequence of steps, right? Computationally, though, what is a step? It's an application of a procedure. Procedure is just another term for function. So many of the most important algorithms of machine learning, sequences of steps, are just compositions of functions. So learning is often via the chain rule. You go forward through a composition of functions, and then you learn using the chain rule. So supervised learning, the use of labeled data to estimate parameters. F is quite often an algorithm model, although F often begins as an equation model, such as logistic regression. Often there'll be an algorithm for estimating the parameters, even when we have an actual equation model. And the backward direction for estimating parameters is almost always an algorithm. And supervised learning is the use of labeled data to predict labels of test data.